Hello. First of all, a big thank you to the organizers for the opportunity to present. When checking through the agenda, I realized that my talk will be diving into a pretty different subject than the rest of the Congress contributions. I hope that it will nevertheless be interesting for you. I will concentrate on classical weed biocontrol in my talk. What is that exactly? Well, weed biocontrol or classical weed biocontrol is directed against plants that invade areas outside of their normal distribution range by introducing natural enemies that can be insects, mites, fungal pathogens from the native range of the plant, with the objective not to necessarily completely eliminate the plant, but to reduce and permanently stabilize the density of this invasive. The expectation is that the natural enemies, or also called biological control agents, are multiplying and dispersing by themselves. The prerequisite for introduction is that they are environmentally safe and effective in controlling the target weed. Environmental safety is, of course, an extremely important aspect, since we do not want to introduce a species that is causing negative effects itself. Likewise, we also do not want to introduce species that are ineffective at controlling the target and might thereby cause negative indirect effects to the local food web. Our center in Switzerland, where I'm located, is specialized in studying the environmental safety and effectiveness of potential agents since over 60 years. We are conducting standardized bioassays and impact experiments for this purpose. I've been personally involved in the testing of agents which can take up to 20 years, involving up to 150 different non-target species. So it is a very long and very thorough process. However, today I will not be talking about these standard testing procedures, but more about additional tools and methods that can be used to improve such pre-release studies further. My presentation will have two main parts. First, I will talk about additional tools and methods that can be used to improve the prediction of the environmental safety of potential agents. And in the second part, I will do the same for effectiveness. First of all, a bit of a historic overview. Since the beginning of weed biocontrol over 100 years ago, the percentage of agents released that did attack non-target plant species continuously declined over time, as you can see on the graphics. And this is due to improved testing procedures, but also due to stricter regulations. So over 500 biocontrol agents have been released overall against about 157 target weeds in 90 countries. And of these, less than 1% have led to non-target impacts that might negatively affect non-target species at the population level. There are currently no documented cases where a weed biocontrol agent led to the extinction of a native species, while there are several cases where the invasion of non-native plants threaten the existence of native species. So overall, a very good safety record. However, as any scientific field, biological control is also evolving and taking on board new developments and techniques to further improve predictions on the environmental safety of potential agents. One quite obvious method is to look which plant species the agent, often an insect, is attacking in its native range. Since this is the host range the agent expresses under very natural conditions, it is a good predictor of the so-called ecological host range once the agent is released. It can also help to prioritize agents for further testing under confined laboratory conditions. A recent example is a study from South Africa on two giant red-tail grasses, indicated by the red arrows on the phylogeny on the left. 47 other grass species, so-called non-target species, were sampled, and 15 herbivorous species recovered. 3 of these were only recorded from the target plants and none of the other non-target grasses, and were therefore prioritized. So instead of testing 15 species in subsequent experimental bioassays, the authors could concentrate on these 3 prioritized species, which was much more cost effective. However, as most methods, also this one has limitations. And in this case, the method is much less conclusive for targets with many indigenous congeners that do not occur in the native range. The second method I would like to present has only relatively recently been developed. As you know, herbivorous insects find their host plant by using olfactory and visual cues. When coupled with an electrophysiological response, such as the reaction of the insect antenna to a specific volatile, one can elucidate the underlying mechanism of host choice behavior of the insect, so why it is attacking a certain plant species and not others. This provides additional data to support the traditional host specificity bioassay results I have mentioned. Another interesting benefit is that it can help to test or expose species that are difficult to obtain or grow, for instance, threatened and endangered species, by non-destructively collecting volatiles in the field, as shown on the below right picture. This is further illustrated in the current example, where our partners of the University of Idaho in the US tested the seed-feeding weevil Mogolonus boreginis, a potential biocontrol agent against hound's tongue, Cyanoglossum officinale, and the federally endangered non-target species Hakelia venusta. You can see the results of an olfactometer bioassay below. The top white bars is the percentage of females that reacted to the olfactory cues of the non-target Hakelia, and the top pink bars depicts the percentage of females which were attracted to the olfactory cues of the target weed, hound's tongue. The bars in the middle are the same for visual cues, and the lower bar when combining both cues. You can see that there was a highly significant preference of the weevil for the target, so the pink bars. In fact, there was zero attraction to the non-target when combining both cues. So this is a nice clear-cut example, but of course it does not always work that easily, and there are also systems where the insect simply does not react at all in such an artificial setup. Plus, since the method is relatively new, at least for weed biocontrol, predictions made with this method have so far rarely been tested in the field. You might think, well, this is all fine, but living organisms evolve, and so couldn't it be that our biocontrol agents, once released in the area, often on another continent where the target weed is invasive, evolves and adapts to a new host once it has successfully controlled the target weed? This is what the following example tried to address: the potential risk of a biocontrol agent evolving a preference for a non-target plant species after its release. The defoliating beetle of Rhaila communa was accidentally introduced from North America to Europe and is very effectively controlling ragweed, probably better known to you under the name ambrosia. However, tests in the lab showed that it can also develop quite well on sunflower, which is, as you know, a commercial crop. In the following study by Heinz Müller-Scherrer and his group at the University of Fribourg in Switzerland, they confined beetles for several generations either onto the target weed ambrosia or onto sunflower. Results showed that in the sunflower cages, beetle densities rapidly declined and no beetles could be found after 3 years. In addition, after approximately 8 generations, the genetic composition of the Rhaila populations kept on sunflower did not change, and neither did the preference of adult beetles or the performance of larvae, which was still high on ambrosia, independently on which plant species the beetles had been kept on. In general, several other pieces of evidence indicate that the probability of a biocontrol agent to unexpectedly switch to a new host is extremely low, and there's currently no indication that this has ever happened in the over 100 years of history of weed biocontrol. I now come to the second part of my talk, so existing and emerging tools to better predict the effectiveness of biocontrol agents before they are being released. Again, I will start with a global overview, which is, by the way, based on a global online database of all releases of biocontrol agents against invasive plants. So before classical weed biocontrol agent can have an impact, it first needs to establish in its new range. The percentage of releases made that led to establishment has been improving more or less continuously since the last 100 years, as you see on the left graphic, and currently lies over 80%. This is likely a consequence of the lower number of more carefully selected biocontrol agents released per target weed. This number has actually decreased from the 60s and 70s, where up to a dozen or more agents were released per target, to only 2 to 4 agents nowadays. In contrast, impact has been much more variable over time. A bit more than 50% of releases depicted by the horizontal line led to medium, variable, or high impact. So this is depicted by the closed circle line, while only 25% of releases led to high impact, where no other control measures are necessary anymore to control the target weed. As indicated by the line with open circles, this percentage has remained relatively unchanged for the last 3 decades. So better predicting and improving the effectiveness of released agents is therefore one of the most important challenges in weed biocontrol at the moment. One of the most commonly used methods to determine the impact and therefore potential effectiveness of weed biocontrol agents prior to their release are experimental setups. These are often done using individually potted plants and exposing them under lab or common garden conditions to the potential biocontrol agent. The advantage is that other factors can also be added to increase the predictive power of these tests, such as intraspecific competition, which is, for instance, the case in the example I included, where the target weed oxide-daisy was exposed to the respective biocontrol agent with or without competition from the grass Poa pratensis. Quite common is also to release different densities of the biocontrol agent, or adding drought as a factor or fertilizer, just to give a few examples. Coming back to the example to oxide-daisy, these experiments can also be used to determine the potential impact that the agent may have on non-targets, in this case Shasta daisy, closely related species to oxide-daisy. And you can see on the far right bars that while there was significant impact on the target, oxide-daisy, the agent had no impact on the non-target. Sorry for that. So these tests under control conditions can provide a very good indication of the potential impact the biocontrol agents may have in the introduced range, but extrapolation to field conditions remains a limiting factor. Another way to predict potential impact is to conduct retrospective analysis. Remember that classical weed biocontrol is a method that exists since over 100 years with more than 500 agents released worldwide, so there is sufficient data available to correlate different agent traits with their impact once released. The following is a summary of several publications, and they found that, for instance, sucking insects are generally more successful than insects from other taxonomic groups. Agents feeding on vegetative plant parts are more successful than ones feeding on flowers, below ground feeders more than above ground feeders, and so on. You might wonder what is meant by the last bullet, agents with few native analogues. Native analogues are species that are relatively closely related to the agent in question and occupy a similar niche. Parasitoids of these analogous species more easily switch to attack the agent in question, thereby reducing their effectiveness. If you have a relatively large number of potential agents, using these relatively crude categories can be helpful for a first round of prioritization. However, not surprisingly, best agent traits differ depending on weed functional groups, so whether the weed is an annual, perennial, tree, a vine. And so agent traits should ideally be combined with plant traits to yield more refined predictions on agent effectiveness. Another approach is to select for specific better traits of the biocontrol agent or to acclimate it to the conditions in the invaded range. As an example, I'm using two species, two agents, a weevil and a murret, released against water hyacinth. Water hyacinth is a serious invader of water bodies, which it originates in South America, has been introduced as an ornamental and is invasive in basically all continents. Biocontrol works fairly well against water hyacinth, but is limited in more temperate regions, since the plant can tolerate cooler temperatures better than the biocontrol agents that should control it. So for the weevil, a more cold-adapted population was released, while for the murret, this was not possible, and it was therefore tried to acclimate it to tolerate cold by rearing several generations of this murret under cooler temperatures. Now, climatic suitability of the agents released can, of course, also be enhanced by ecoclimatic models that can, for instance, inform where and when to survey for potential agents and where and when to release them for best climate match. Similarly, species distribution models can help to select candidates that likely cover a large distribution range of the target and which will likely control it across its entire environmental amplitude. The last method I would like to present does not focus on the agent, but on the target weed. Again, it's quite logical that biocontrol effectiveness can be enhanced by selecting agents that attack the phenological stage of the target weed, which is most vulnerable, the so-called Achilles heel of the plant. So the stage with the highest impact on the intrinsic rate of increase of the plant. However, this is easier said than done, since it necessitates the development of a detailed demographic model of the target weed, which can be quite resource intensive. We did that for garlic mustard, a plant native to Europe, invasive in North America. The model predicted that the root-feeding weevil Pseudorhynchus scobicollis would have the most significant impact on population growth of the plant, and this agent was subsequently prioritized for release. At this point in time, densities are still too low to confirm model predictions. Limitation of this method is that, as already mentioned, it is time and labor intensive, plus it is questionable whether predictions can be upscaled over the whole geographic range of the target due to large site by year variations. So I'm coming to recommendations. If a relatively large number of potential agents is available, prioritization should focus on the likely effectiveness of agents. Once host-specific agents have been identified, the best adapted agent or agent population should be selected for release. Seemingly oligophagous agents should not be dismissed outright, but more studies conducted along the lines as I presented. Collection of systemic post-release data on agent safety and effectiveness should be standard. Without such data, predictions made pre-release cannot be verified. To further and experimental hypothesis-driven post-release monitoring and retrospective analysis of long-term data sets is recommended to further enhance the environmental safety and effectiveness of weed biocontrol. Some concluding remarks. Classical biocontrol is practiced since over 100 years. Reports on potential population level impact on non-target plants are very rare. With current safety standards in place, the environmental risk of introducing classical biocontrol agents is negligible. However, skepticism around the safety of classical biocontrol persists, and more work is needed to improve and predict agent effectiveness. And this work is ongoing. And lastly, just so that you believe that wheat biocontrol can actually work, here a couple of before-after pictures and some cost-benefit analysis will show that this method can be extremely cost-effective. In case this presentation sparked your interest and you would like to know more about wheat biocontrol, please don't hesitate to contact me or visit our website. Thank you very much.